All right, class, this is a section on chapter 10, which is fluids. We'll be doing with density, specific gravity, pressure, fluid pressure, Archimedes principle, and then finally their Bernoulli equation. So we're going to start, and hopefully you'll have your textbook in front of you, because we're just going to follow the textbook. I'm not going to try to read the textbook too, but I'll point out important things and I'll give you examples. So on page 10-1, we start out talking about density. Now the density of an object is its mass divided by its volume. So the example of density would be water. Water has a density of about 1,000 kilograms per cubic meter, 1,000 kilograms per cubic meter. Anything that's less dense than water will float. For example, a piece of wood will usually float in water. Anything that's more dense than water, like an iron hammer or something which is made of lead, which is a density about 11 times that of water, it will sink. So this is what we have. We have the density and this mass divided by the volume. So I'm going to start out by doing a very simple problem. Suppose you have an object which has a mass of about 7,000 kilograms. And suppose its volume is 1 cubic meter. Then its density is going to be 7,000 kilograms per cubic meter. And that has a density of about 7 times that of water, and so it would float. I mean, it would sink. It definitely would sink. So that's our density. And beside that, the symbol for density is the Greek letter rho. Looks like a P, but it's rho. And so this formula could be written this way. Rho is equal to M divided by Z. So something more dense than water will sink, something less dense than water will float, and so this one would sink. Now the density of water, pure water, is about 1,000 kilograms per cubic meter. So that's the density of water. So in this case, this object is about 7,000 kilograms per cubic meter, which means it's 7 times more dense than water, it will sink. Now on page 10-1, after we talk about density, then we talk about specific gravity. Well, specific gravity, S-P-E-C-I-F-I-C, gravity, G-R-A-V-I-T-Y, and that's the density of an object divided by the density of water. Density of water. All right? So in this particular case, the density of this object is 7,000 kilograms per cubic meter. The density of water is 1,000, pure water is 1,000. And so this comes out to be about 7.0. So anything that's greater than 1 will sink, and this object would sink. And usually we abbreviate specific gravity to SG. And this actually is on page 7-1. Now I hope you actually have your textbook in front of you, because we're just going to follow the textbook. So the next thing we have to do is we have to talk about, there's an example here, example 10-1, which you should review. So review. (10-1) on specific gravity. All right? Okay, now the next topic we have to talk about is pressure. So I'm going to turn this page over. And we're going to talk about pressure. And pressure is just force divided by area. Now this is actually on page 10-2. Towards the middle of page 10-2. And just to give you a very simple example of this, I'm going to go back to the problems at the end of the chapter. And there's a problem here. It's on page 10-15, and it's the problem number 2. So page 10-15. Problem 2. And this problem says a 100 kilogram student, and he's standing on an area on his feet, actually 1 foot, and 1 foot is 30 centimeters long and 18 centimeters wide. We want to find out the pressure that he's exerting on the ground. So I'm going to take his mass, which is 100 kilograms, but to figure out his weight, we have to multiply that by 9.8 meters per second squared. And the area of his foot, it says is what, 20 centimeters, 30 centimeters by 18 centimeters. Well, 30 centimeters would be 0.13 meters. And the width of the thing was 0.18 meters. So now you get out your calculator and you work that problem out, and you should find out this one's out to be about 18000. And that's newtons per meter squared. Now you're familiar with power of 10 notation, so for power of 10 notation, you move the decimal point 1, 2, 3, 4, and so this will be written as 1.8 times 10 to the 4th newtons per meter squared. Well, in physics, we love to name these things after people. And so there's a fellow named Blaise Pascal. He's a Frenchman, and they decided to name it. He did a lot of work on pressure, and so they decided to name it after him. And so this would be 1/18,000 pascals, and that's abbreviated PA. So that's page 10-15. Let me write that again. And it's problem number 2. All right? Now, in terms of pressure, there's 2 types of pressures that we talk about. One pressure is called gauge pressure. G-A-U-G-E. And the other type of pressure would be the absolute atmospheric pressure. Now, if you're familiar with atmospheric pressure, because that's the pressure acting on our bodies, and if you had chemistry, you would know that's about 14.7 pounds per square inch. That's the atmospheric pressure. 14.7 pounds per square inch. And actually, that, in terms of newtons per meter squared or pascals, that would be 101,300 pascals. Now, most of us have cars, and the pressure in your tires, that's called gauge pressure. In other words, use a gauge to measure that pressure. And so your car, that's usually about maybe 32 pounds per square inch, or PSI. Now, the combination of these two is called the absolute pressure, the total pressure. So the absolute pressure here would be equal to the gauge pressure, G-A-U-G-E, plus the atmospheric pressure. And the total pressure here of these two would come out to about, I think it's about, total about 300,000. And that would be newtons per meter squared. And that would be 300,000 pascals. And that's the absolute pressure or total pressure in that particular case. Now, there's a problem here in the book, and I'm going to turn the page again. All right. So I'm going to go into the back of the chapter, and I'm going to look for another problem, and this is actually problem number 4. Maybe problem number 5. Okay. Now, problem 5 is on page 10-16. This says the absolute pressure at the bottom of a swimming pool. So you have a pool of water like this, and you have the pressure acting on the bottom. Now the gauge pressure is just due to the water. In that case, the absolute pressure would be the water pressure on the bottom plus the atmosphere. So that would be the gauge pressure right there. So the gauge pressure in the case of a fluid like this is given by another equation. This equation is given by rho g h. And most of you have been in swimming pools, and if you dive to the bottom of the swimming pool, you can feel it on your ears. In other words, the pressure on your body increases with depth. Now the density of water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. And this says the swimming pool is about 5 meters deep. And so the gauge pressure in this case would come out to be 1,000 times 9.8 times 5, and that should be about 49,000 newtons per meter squared, and that would be 49,000 pascals. Now if you want to know what the absolute pressure is, and that's what the problem says, it says determine the absolute pressure at the bottom of the pool, then the absolute pressure that's going to be equal to the gauge pressure, 49,000 pascals, plus it's going to be equal to, plus the atmospheric pressure, which is 101,300. So 14.7 pounds per square inch converted over to the SI units, the International System units, would be 101,300 pascals, or newtons per meter squared. And the two of them should come out to about 150,000 pascals, and that would be the absolute pressure. And I think I'd like to take a little break right now.